Hey, hi, nice to meet you all. My name's Liam, and I'm here today to introduce to you guys Zelana, which is a ZK SVM rollup built on Solana. So just a quick intro to our team. We're comprised of 5 members. We're all been building with Rust, and we have a full stack background. Our background also ranges between like cybersecurity all the way to finance, and we have a breadth of skill sets that we combine together to implement this project. So without further ado, I'll just describe what Zelana is. So Zelana is, as mentioned before, a ZK-rollup built on SVM. We made use of Anza's SVM API to implement the rollup, and then what we're doing is we are executing transactions off chain and proving correctness with using ZK snarks. So what we do is we batch like a series of transactions, and we create our proofs, and then we settle on the SVM layer 1. So what was our motive behind this project? We came across Anza's blog about the SVM new API, and we understood that we can improve like network latency and throughput through the likes of proving like state transitions inside a rollup and then settling on chain. So then this sparked an idea to create ZK circuits within our rollup and verify, and then what we thought was we can improve the likes of scalability, so improve the throughput through this design. We can expose security as well, so we thought about creating bespoke ZK circuits that are difficult to integrate with through applications. And then of course we thought interoperability and efficiency were other areas to focus on for our ZK implementation. So this is the architecture. You could think of this as 3 core components. We have a rollup client, which could be connected to a front end, and then we have an API layer that's used to submit transactions, get transactions. Inside the rollup core, we have something called a sequencer, which is used to batch the transactions, and it connects to an SVM API. And then we send the proofs we send the batches into a proof generator, which creates a ZK snark proof, and then we verify on chain through a verifier program. So I'll let Dave chime in here, because I know he's been working on the proof generations intimately.
Right. Jim, guys, can you hear me?
Yep.
Okay, so I'm going to be talking about the proof generation, which is the rollup core. So literally, the rollup core just revolves around processing transactions, proof generation through second circuit, and also proof management, which includes storing the proof, tracking the proof states, and updating the state, and also retrying field proofs. So the second circuits were specifically built for system transfer proving, and we have 2 circuits, which is system transfer.secom and batch system transfer.secom. And the system transfers is a circuit that actually validates the individual system transfers by proving that transfer amounts fall within acceptable ranges. It also verifies transaction signatures and confirms account balance updates. While the batch system transfer is actually also very similar. I extended the circuit to handle 3 transactions simultaneously. So it generates 1 proof for every batch that contains 3 transactions. So yeah, both circuits generates brought 16 proofs, and demonstrates that our rollup transactions were correctly executed. So yeah, we also have settlement worker, which posts generated proofs to DevNet for verification, and verifier program verifies those proofs. And when the settlement succeeds, the settlement worker updates the proof status. We have different proof status, which can also be called proof states. We have generated, we have verified, we have failed, and we have posted. So literally, generated is when a proof gets generated using our prover, and verified is when a proof has been verified, and posted is when we send the proofs for settlement, and failed is when a proof fails to verify. So and our rollup DB has a background worker that actually queries every 5 minutes for identifying proofs that failed during settlement, and we have like a maximum limit of 3 attempts for retrying failed proofs. So passing back to Liam now to continue. Thank you.
Cool, thanks, David. So I think we're now ready for a technical demo. So I'm now going to pass it on to Glacier.
So as Glacier pulls this up, I want to say one quick thing. Listen to the different accents of the people on this team. They are literally all over the world. It's one of the things we're most proud of is we create super tight, galvanized, familial teams in a short period of time that get this stuff done. And I'm super proud of that. Go ahead, Glacier. Rip it, sir.
Yeah, GM guys, hope you can see my screen.
We can, but you got to take the share anyway. There you go.
Yeah.
Perfect.
So this is a simple front end that we built. So we can do a simple health check. We can send 3 transactions in a series or 1 transaction here, and we can also see all the PDAs that were created earlier, which through our on-chain verifier. So if I'll just do a simple demo here, you can put a pub key here, some random RAM ports. Then it takes the signature from Phantom wallet, and we also get the block hash from here just to prepare the transaction. Yeah, and we settled it to our rollup core, which is running in the background, and more details will be given by Jivan for that.
I'll just show the demo through the CLI. Whoever loves the CLI. So I have the rollup code already running, and I just execute the client. Yeah, we will be getting the info of the rollup code, like what and all is running. And so then, like, we got the settlement hash, and now we can just go through the Explorer and we can just check the transaction. Yeah. So we have the on-chain verifier, it has an instruction called verify.16.2. So what it does is it just verifies all the batches and settles on the on-chain. Yeah.
So we got an overview of the front end, and we saw a proof getting verified on-chain using our Groth 16 implementation. And as Dave said, we're using Solana BN254 syscall for this. So our potential plans for the future, we're looking to introduce more features and improve the infrastructure. So we care about privacy here, so we want to expose like more ZK circuits for application use, potentially integrate an RPC layer for our own bespoke RPC methods, expand our rollup DB to make it more scalable. And I think Mono also has some great thoughts as well on this, so I'll let him chime in here.
Yeah, the last thing I wanted to add was that using Circon and Snark.js is a bit clunky. and we've been looking at alternatives like G-Snark and just making native provers by using the arc crate from Rust, which should be potentially faster than using Go, which is the standard of ZK Snark. But yeah, we'll see how that goes.